Hi, good afternoon. Let's get started. So, for today, I have one problem that I prepared, and after that, we can give you opportunity to ask any questions you have from the homework. If you don't have questions from the homework, I can just go down the list of homework questions and kind of give you a hint of what to do on some of the problems. Not obviously not going to have enough time to solve them, but at least give you some instruction of what you should be doing for each problem to make it easy for you. So when I'm going through this example, so if you have any questions for the homework, definitely think about it and let me know. So the example that we're going to look at is we're going to solve this initial value problem with y double prime plus y equals f of t. This initial condition y of 0 equals 0, y prime of 0 equals 1. And the f of t is given as piecewise function. F of t equals 0 for t is less than 2, greater or equal to 0. F of t is t squared if t is greater or equal to 2. So that's what's given. It's an initial value problem. We're going to solve it using Laplace transform like we did before. So the first step, step 1, we're just going to find the Laplace transform of the differential equation. So that would be Laplace transform of y double prime plus y. And then the right-hand side is going to be Laplace transform of f of t. The left-hand side, if you find the Laplace transform of each one, you get s squared capital Y of s minus s lowercase y of 0 minus y prime of 0, and then plus capital Y of s. The right-hand side, we're going to have to do a little bit of work because it's not straightforward. It's a piecewise function, right? So that's a heavy lifting work. So let's leave it for now. Let's focus on the left-hand side and finish it. So plug in the initial condition. This is going to be a 0. This is going to be a 1. So we just end up with s squared, capital Y of s plus y of s, so plus 1 capital Y of s, and then minus 1. So that's the left-hand side. We need to know the right-hand side before we do more work. So let's just kind of leave it there. Okay, so now let's find the Laplace transform of f of t, which is, if you were to graph it, the first piece is just going to be 0 from 0 to 2. And then the second piece is going to follow the curve t squared. And if you remember, t squared is a parabola centered at the origin. So that tells us that for the second piece of the function, it's going to follow this dotted yellow line. And that's an open circle. But we can connect this with a vertical line. So that's what the shape of the function is if we were to graph it. Okay, so we want to find the Laplace transform, but at the beginning, we're going to have to take the f of t and then find the Heaviside function expression for it, and then take the Laplace transform. So what I did is that I factor out anything that's non-zero. So t squared is a non-zero, we can factor out. So f of t is equal to t squared. The factor will give us when the function is 0. When we take out t squared, we still get a 0. T is between 2 and a 0. And then when function is t squared, we end up with a 1 when we take out a t squared. That's for t is greater or equal to 2. So now if we focus on this piecewise function, we can figure out the corresponding Heaviside function. But let me plot it, just kind of get a picture. So from 0 to 2, we get 0 here. And then from 2 to infinity, we get 1. So we get this shape. So we begin with 0, but then it goes up at t equals 2. So the heavy side function for that is ut minus 2. Just one t, there's nothing else attached to it. Therefore, the f of t, we can write it as t squared times ut minus 2. Any questions about what I did over there? So after we successfully express f of t in terms of Heaviside function, we can find the Laplace transform. The Laplace transform of f of t, which is Laplace transform of u t minus 2 t squared. I'm flipping the order of those two terms. And then that we can use the rule we talked about last time when we have, just recall that the t translation rule, if we have Laplace transform of u t minus a f of t, and that's the u part will give us the e to the negative as. And then we take the Laplace transform of f of t, but with t being replaced with t plus a. So that's the extra work we have to be mindful of. So now we're going to, in the example we have, the u part, t minus 2, will become exponential with a being 2 here. So that will give us e to the negative 2s. And then we end up with Laplace transform of t squared. But remember that t squared, the t there has to be replaced with t plus a, so t plus 2. Right? So from here, what do? We're just going to substitute the t in t squared with t plus 2. And then we're going to find the Laplace transform of that. So I'm going to be a bit lazy by just only focus on this part. So that becomes Laplace transform of t plus 2 squared. And that further becomes, if we want to find the Laplace transform, we need to expand it. So that's going to be t squared plus 4t plus 4. And then don't forget, I'm just going to bring everything together. I still had this e to the negative 2s in front. So now I can find the Laplace transform of the 3 terms. And in front of it, I have e to the negative 2s. So e to the negative 2s times t squared will give me 2 factorial over s to the 2 plus 1, so s cubed. 4t will give me 4 over s squared. And the last 4 will give me, is 4 times 1, so 4 over s, 4 times 1 over s. So those are the Laplace transform. Here we have this highlighted terms is the Laplace transform of f of t. And we're going to use that in the differential equation when we apply Laplace transform. So this expression goes to here. So now what do we have? We have, going back to the left-hand side, we had this part. And on the right-hand side, we just funded by doing this extensive work. So we get e to the negative 2s bracket 2 over s cubed plus 4 over s squared plus 4 over s. And if you look at it, we end up with this equation, right? This equation, we have s, we have y of s. So we can move on to step 2. We can solve for capital Y of s by moving 1 to the right-hand side, divide by s squared plus 1. So we get y of s is equal to 1 over, so when I move the 1 over, it becomes 1, but when I divide by s squared plus 1, I get this fraction. But I also had e to the negative 2s, 2 over s cubed plus 4 over s squared plus 4 over s. And I'm going to take that product, divide by s squared plus 1 as well. So this is y of s. The next step is finding the inverse Laplace transform to get y of t, but we should simplify this first if we can, because we can't just finding the inverse directly. So let's simplify. When I see simplify, I simply means that we need to simplify this part. The rest, we can just leave it the way it is. So if we want to simplify this, the first thing we need to do is we need to common denominator in the numerator. So that will give us y of s. So I'm just going to write down what I end up with at the end, which is 1 over s squared plus 1 plus e to the negative 2s times this fraction, which is 2 plus 4s plus 4s squared divided by s cubed times s squared plus 1. It doesn't really help us a lot, right? But maybe it's going to help us in the next step. So the next step with some complex fraction like this is that we have to find partial fractions. So again, I'm not going to show all the detailed work. I'm just going to jump into the final answer after finding partial fractions. So that's a 1 over s squared plus 1 doesn't change, plus e to the negative 2s doesn't change. And the fraction becomes 2 over s plus 4 over s squared plus 2 over s cubed, and then minus 2s plus 4 over s squared plus 1. And this is pretty good. So now we can actually try to find the inverse, because we get 2 over s, 4 over s squared, 2 over s cubed. That's all fine. Even though the last fraction is still complicated, we can split into 2 fractions when we need to. So it's not that bad. So step 3, find y of t by using the inverse Laplace transform of capital Y of s. So y of t is equal to inverse Laplace of this expression above. So I'm going to apply inverse Laplace to the first term, to the product. So inverse Laplace of 1 over s squared plus 1. And by just looking at it and I'm thinking, oh, it looks like something in the table. So maybe we can use the table to find it. Plus inverse Laplace of e to the negative 2s times 2 over s plus 4 over s squared plus 2 over s cubed minus 2s plus 4 over s squared plus 1. So what do we do with this product then? The trick is that this is actually a good thing when we have e to the negative as, with a being 2 here. This is where we can use the inverse t translation, which is says if you have inverse Laplace transform of, so recall e to the negative as times some expression is s, and the e to the negative as will become a u function, t minus a, and then we just going to find the inverse Laplace of the remaining f of s, but there's an extra string attached to it. So at the end, we need to replace t with t minus a. That's the very end. So we're going to use that rule for the second part. So again, the first one, I'm going to leave it. So plus e to the negative 2s becomes u t minus 2 to its the a value, and then inverse Laplace of this remaining. So that's a 2 over s plus 4 over s squared plus 2 over s cubed. I'm also going to split the last fraction at this point. So that's a negative 2s over s squared plus 1. And then we have negative 4 over s squared plus 1. And at the end, t will go to t minus 2. Any questions about what I did? So the process is similar to what we did before. You find the Laplace transform, you solve for y of s, and then you find the inverse Laplace transform. But obviously this problem is difficult because of the f of t is not easy. So from here, what we're going to do is that we're just going to find the inverse Laplace transform of this part. And after we've done that, we're going to plug in t minus 2 for t. And everything stays the same for now. Well, actually, I can figure out the inverse Laplace of 1 over s squared plus 1. So that's just going to be sine t plus u t minus 2 times. And if I find the inverse Laplace for this expression, I have 2 times the inverse Laplace of 1 over s plus 4 times the inverse Laplace of 1 over s squared. This one I'm taking a shortcut here, so I'm not going to pull out the 2 because I remember from previous steps, Laplace transform of t squared give me 2 over s cubed, so I'm going to leave it. So that's going to be inverse Laplace of 2 over s cubed. That will give me t squared directly. But it's safe to pull out the 2 and the negative 2 and the 4 and the negative 2, negative 4 from other terms. So minus 2 inverse Laplace of s over s squared plus 1 minus 4 inverse Laplace of 1 over s squared plus 1. And at the end, t goes to t minus 2. So let's try to finish this problem here. So we get s sine t plus u t minus 2. Then in the bracket, we have 2 times 1, just 2, plus 4 times t. Oops, I don't know what happened. And then plus t squared, and then minus 2 cosine t plus minus 4 sine t. And then that's the end, but we have to replace t with t minus 2. So last step, we get sine t. This t doesn't change, and then the u part doesn't change. 2 plus 4 times t minus 2 plus t minus 2 squared minus 2 cosine t minus 2 minus 4 sine t minus 2. That's it. That's the answer at the end. It's a lot of work for some examples, but again, try to understand the big picture, right? Like, what's the first step? What's the second step? And then try to remember that what you have to do if you have some function that's not simple one. You use the S translation, you use the T translation. Make sure you apply them correctly. Any questions on that? if you have any questions, feel free to unmute yourself and then, you know, ask or put in the chat box. It's not an easy problem. But it's a good practice problem to do because it's really used a lot of techniques with the Laplace transforms. So if you don't have questions, I want to point out one thing about the final answer here. You can rewrite this final answer instead of using Heaviside function here. We can just write it as a piecewise function. So note this Heaviside function t minus ut minus 2 is equal to 0 if t is between 2 and 0. Is equal to 1 if t is greater or equal to 2. So we can use that to rewrite this final answer. So the first piece is plug in 0 for u t minus 2 for t is less than 2 greater or equal to 0. So y of t equals sine t plus 0 if we put 0 there times this bracket term. And that's for t is greater or equal to 0, less than 2. And then we know if we take anything multiplied by 0, we get 0. So that part we really don't keep. We just get sine t. So that's the first piece of the piecewise function. The second piece is for t is greater or equal to 2. We're going to take 1 put in there. So we get sine t plus 1 times bracket 2 plus 4t minus 2 plus t minus 2 squared minus 2 cosine t minus 2 minus 4 sine t minus 2. And obviously we don't have to write the 1 times. We can just erase the 1 there. And we can even drop the bracket in this case. So this is for t is greater or equal to 2. So this is also a acceptable answer in terms of piecewise functions. Does that make sense with this problem? Any questions on it? It's long and lengthy. I know that you probably have some questions in the process. Feel free to ask them here.
So for the Laplace transform of the Heaviside, t goes to, just for clarification, t goes to t plus 2, but then for the inverse Laplace, when using the Heaviside, it goes to t minus 2.
So if I understand correctly, in the last step, right, in the step 3, you said if, sorry, go ahead.
Oh no, sorry, actually I think I just, never mind, because I did flip for some reason, because the Heaviside goes to the exponential function. I see that's when it goes to t plus a, and then the opposite, it goes to t minus a.
Exactly, right. So for the t translation, so when we find the Laplace transform, we're going to have t goes to t plus a first, right? And then when we apply the inverse, we're going to have to add a t goes to t minus a as an end after we find the transform. So, right, so different substitution for t in this the translation and the inverse.
Okay, thank you.
Yep, good point. Exactly, Joe. So just be careful with the plus a or minus a, and then know when to plug in those t substitutions. Any other questions? So when you see a problem similar to this on the exam, I don't know what kind of problem will be on it, but from what I was told that there'll be one problem that's solving initial value problem using Laplace transform. So it's similar to what I have in the left-hand side, you have y prime, y double prime. The right-hand side is some function. It could be piecewise function. It could be something simple. It could be something that requires S translation. So that's one problem. Depends on what f of t is, right? And the second problem on the exam could be just like a homework problem. Number one, have A, B, C, D different parts, right? Some parts ask you to find the Laplace of, some part ask you to find the inverse Laplace transform. So it's really just a mix of smaller problems into one problem. So that's a kind of a format for the exam. I think I mentioned it before, the table of common Laplace transforms will be given. The S translation, the T translation, those rules will be given. So you don't need to memorize them, but you do need to know when to use it, right? Keep that in mind. The next thing I want to do is I want to go over some homework questions that you might have. Any questions from looking at the homework problems? So for homework problems, number one has 4 parts. I want to kind of just give you a hint how to do each of them, at least tell you what rule to use. So for A, is asking you to find the Laplace transform of 2t plus 3 times u t minus 4. I believe that's a correction. The correct problem. I might wrote it down incorrect, but anyway, that's a sort of the question. So if you see something like this, you want to find the Laplace transform of some function, and if you see u t minus 4 in there, that's an indicator that we're going to use t translation. And then this part will come out and become a exponential. So e to the negative as. You kind of have to know what a is by looking at ut minus 4. So this will tell you what a is. Right? And then what we do is we just take the Laplace transform of the remaining function, 2t plus 3. But here, instead of just leave it the way it is, we have to apply a substitution, which t goes to t plus a. And then you should know what a is by now. So that's just the hint I want to give you. So apply the substitution first before you apply the Laplace transform. Feel free to stop me or ask questions at any time when I'm going through this. So B there, which is asking you to find the Laplace transform of e to the, I remember, so that's going to be e raised to the negative 3t, I believe, t minus 5 squared. So I think that was a question. So if you have something like this, so here we begin with e to the negative at, and it's very important to pay attention. It's a function of t there, not s, because that could be confusing. It shouldn't be s. When we find the Laplace transform of some function of t, it should be t there. So here we have exponential e to the negative at. This should be an indicator that we need to use S translation. So in S translation, the first thing we do is we pull out this, we just put it outside. Like, don't worry about it. We write down the remaining. So that's a Laplace transform of t minus 5 squared. But where do we put the translation? The translation is noted as S goes to S minus A. And you can figure out the A from there. So the translation is not an expression. It just tells us that at the end, the s will be substituted with s minus a. Let's keep that in mind. And also, I want to add a note to this problem that you want to expand it first before you find the Laplace transform in the next step. So that's B. C, which is finding the inverse Laplace transform of 2s plus 3 divided by s squared plus 6s plus 34. It looks like it's simple, just a fraction, right? You might find partial fractions. In fact, it's not easy to find partial fractions here because it's already in the simple fraction form. So what we do in this problem is that we convert the denominator by completing the square. So that becomes inverse Laplace of 2s plus 3, but the denominator, we're going to write it as s plus some number squared plus a remaining number. Let's call this number hashtag, whatever that is, right? So we need to find it and put it into this form. And then this is not it because the denominator has a s plus hashtag expression, but the numerator we only have s. So we need to make sure they're the same. So in the following step, what you're going to do is you're going to find the corresponding expression for the numerator, turn it into 2s plus hashtag plus some number, and denominator will be s plus hashtag squared plus some number. And from here, the benefit of doing this is that, so now we have s plus some number squared. In the numerator, we have s plus some number squared. We can replace both at the same time with a new s. So that will be Laplace transform of 2 times this new s. I'm going to call it s hat. You can just call it s or some notation plus a number, and then probably not s hat, just keep it s. There's a line in the middle. And divide by s squared plus a number. And note that in this process, what we did is that we converted s plus this hashtag into s, this new s. So that's what we did, we convert that. And in the following step, if you apply the inverse s translation, you know this becomes an exponential. That just becomes e to the negative hashtag t, and then we still have this inverse Laplace of this 2s plus a number divided by s squared plus a number. We have to find the inverse Laplace transform. So I apologize if my notation is confusing with hashtag and space, but that's sort of the picture. And at D, we're finding the inverse Laplace of, I forget exactly how it was written in the homework, but it was something like e to the negative pi over 2s times s over s squared plus 4. So for this one, when we finding the inverse Laplace transform, and inside we have an exponential expression with s. So in this case, e to the negative pi over 2s, right? This is the indicator that we're going to use t translation inverse. And then this one we can pull out and then make it into u t minus a. You have to figure out what a is from the expression. A is pi over 2. And then find the inverse Laplace transform of the remaining s over s squared plus 4. And don't forget at the end, t goes to t minus this a. So that's sort of like the something to keep in mind, because you might have problem like this on the exam, ask you just to find the Laplace transform or maybe the inverse Laplace transform of some function You look at it like, oh, looks like we're going to have to use this rule. Depends on the path we make. But I do want to point out that B and D, they look similar if you kind of just ignore the difference in the Laplace and inverse Laplace transform. If you just look at the curly bracket, it's like, oh, both have exponential. Which one do I use? So that's why you have to be careful. If it's a function of t and the Laplace transform, you're going to use S translation. If it's an inverse Laplace transform with a function of S, you're going to use T translation, the inverse. So that's something to watch out for. Any questions about number 1 in the homework? Number 2, 2A. So 2A I have, the question is, given that f of t is equal to sine t, t is between pi and a 0, and a 0 for t is greater than pi. Greater or equal to pi. So it asks you to sketch a graph, and it asks you to find the f of t in terms of Heaviside function. And also it asks you to find the Laplace transform of f of t. So sketch it, we can do that, which is from 0 to pi, it's just going to be sine, and the more than pi is going to be 0, so that's a graph. And if we want to find the Heaviside function, so what I do is I just factor out the sine of t from both p's. So f of t is equal to sine of t. If we take out sine of t from itself, we get 1. And then if we take it from 0, we get 0, right? So that's t equal to pi. T is between 0 and the pi. How do we figure out the Heaviside function for this piecewise function? Well, we can graph it, see what it looks like. Maybe that will help us. So from 0 to pi, we get 1. And then from pi to infinity, we get 0. So we kind of have this graph that you go somewhere, start with somewhere, and then drops, right? So that one, what I do, there's a couple of ways. One thing is that I can try to complete the left side at t equals 0, it goes up. And then at t equals pi, it goes down. So that becomes u t minus 0 minus u t minus pi. If we have a graph that goes up and then coming down to 0. That's one way. Now, another thing that we could just maybe remember or use it is that this part, ut minus 0, for t is greater or equal to 0 as given in this example. So that's always going to be 1. So that you can write as 1 minus ut minus pi, because we already given that t is greater or equal to 0. So that's always okay to use. Just use 1 instead of ut minus 0. But either one you use, if you follow the correct step, it should give you the same answer. So now we can write down f of t is equal to sine t times, I'm going to use the second one, the 1 minus u t minus pi. And then we can find the Laplace transform from here. The first part is Laplace transform of sine t. We know that based on the table. Minus Laplace transform of the second part, which is sine t times the u. So u t minus pi times sine t. So here, the first part, like I said, I'm confident that you can find what that is. Now the second one, because we have a u there, so again, that's a t translation, right? So let's pull that out. So that's going to be e to the negative a's pi. So negative pi t, sorry, negative pi e to the negative as, negative pi s, and then Laplace transform of sine t, but with t replaced with t plus a pi. And I'm going to be lazy. I'm just going to focus on this Laplace transform part so that I don't have to write a lot. So that's going to be Laplace transform of sine t plus pi. And then how do we find it? We have to expand that using sum of angle formula. So that's a sine t cosine pi plus cosine t sine pi. The benefit is that we know what sine pi and the cosine pi are. If we put in, it's pretty nice because sine pi is 0, cosine pi is -1. So what we end up with putting all together is Laplace transform of sine t minus e to the negative pi s Laplace transform of negative sine t. And then you can pull out the negative and find the Laplace transform of sine t. So I'm not going to finish the problem. I'm going to leave it there and for you to kind of go back and try to figure out on your own. 2b, I already did one example last time, very similar to it. So if you don't know how to do that problem or get stuck, feel free to refer to the example I did. 3 and the 4, I'm not going to do them because they're similar to the example I did earlier today. In the given time, we're almost done here. I want to kind of mention number 5 here, which is solve initial value problem with y double prime plus 4y prime plus 5y equals delta function t minus 2 pi. It has a delta function, it's new, but just think about delta function is a special function. The Laplace transform of delta functions are very nice. So here we have y of 0 equals y prime of 0 equals 0. That's the initial condition. So to do it, the first step is we're going to find the Laplace transform of the left side and also the right hand side. Laplace transform of delta function t minus 2 pi. And the Laplace transform of delta function is given in lecture. So that's let me just note, we call that Laplace transform of delta t minus a is just going to be e to the negative as. So we just have to identify a is 2 pi in this case and then put in there. So the left hand side, whatever it is, the right hand side will become e to the negative 2 pi s. And I'm sure you are confident enough to figure out the left hand side by using the initial condition and also the table of Laplace transforms. So at the end, we end up with, what was it? S squared plus 4s plus 5 capital Y of s equals e to the negative 2 pi s. And from here, we just do exactly what we did before. We're going to solve for capital Y of s, which is e to the negative 2 pi s times 1 over s squared plus 4s plus 5. So what do we do next? We can find the inverse, but it's not easy. So we're going to have to do some prep work. So we need to find partial fractions for this. And that will give us, a fraction with a and a b with different denominators. No, numbers. I'm just going to use parentheses rather than the partial fractions. And now it's okay to find the inverse. So the solution y of t equals inverse Laplace transform of capital Y of s. And that's going to be inverse Laplace transform of e to the negative 2 pi s times this partial fractions. Right? So what do we do next? Well, we begin with the delta function. Now we end up with this. But this, if you look at it, it's actually nice because, well, even though we're not familiar with it, but it's not that bad, right? Because this is the exponential with s in the exponent. And that means we can use the inverse rule of t translation. And that will give us u function, t minus a is 2 pi in this case, and then inverse Laplace of this remaining part, a over this denominator plus b over this denominator. And don't forget, in this process, when we apply the inverse t translation, the t will goes to t minus a in the very end, so a is 2 pi. So after you find the partial fractions, I'm pretty confident that you can figure out the inverse Laplace of each one of them, and there you have it. Don't forget to plug in the substitute the t with t minus 2 pi. So okay, so here's a question. Can we not complete the square rather than do partials? You mean like let's see. If you so for this particular problem, I think it's easier if you find the partial fractions. But if you want to if you're thinking about from here, if you want to oh no, wait. Actually, I screwed up. I probably did. Ah, yes, you're right. I did this wrong completely. Partial fractions can even factor this. Yeah, I did it wrong. Sorry. I have to go back and double check. I think instead of finding partial fractions, you have to complete the square. For this, that's a very good point. I didn't even, I did the problem quickly. I don't think I did it correctly. Now I'm looking back. I don't think we can factor the denominator. We have to complete the square and then go from there. We're going to have to end up using the inverse S translation at the end instead of using partial fractions. Yeah, good point. Very good. Excellent point. Thank you for pointing that out. Any other questions on this, on the homework problems? All right. On that note, I'm going to let you go. And I'll see you on Tuesday. Good luck on the homework. Like I said, if you get stuck on the homework, just look at the notes from lectures and the recitations. They're all recorded. And also feel free to let me know. I'll try to get back to you, but it's a very busy weekend for me and the following week. And also tomorrow. All right, take care, everyone.